Welcome to The Explainer. Today, we're jumping into a really cool new paper from Sakana AI. They're tackling one of the biggest headaches in AI right now. It's surprisingly short attention span.
So let's get right into it. We've all seen AI do these incredible things, right? It can write poetry, it can generate code, the whole shebang. But have you ever tried to give it a 200-page legal contract or maybe a super long chat history? Suddenly, its performance just falls off a cliff. It gets lost, it forgets really important details, and it just fails at the very things we need it for. This whole issue has a name. It's called the long context problem. And honestly, it's one of the biggest hurdles holding AI back today. You can almost think of it like the model has a very, very expensive form of amnesia. The longer it reads, the more it forgets, which makes trying to reason over long documents practically impossible.
Okay, so you might be thinking, well, why don't we just train the models on longer and longer stuff? And that's the obvious question, right? But it turns out it's incredibly hard to do. There are two huge reasons. First, just finding enough good, clean, really long documents is a massive challenge in itself. And second, the cost. The compute cost is, and I'm quoting the researchers here, brutally expensive. That's because the attention mechanism that makes these things tick gets exponentially more demanding the longer the text is. Because of those crazy costs, the real goal, kind of the holy grail here, isn't just longer training. It's something called length generalization. The idea is, can you train a model on a relatively short piece of text, say 4,000 words, but then have it work perfectly fine on a document that's 10 times longer, without ever having to retrain? But here's the tough reality for most models out there today. When you try to push them past the length they were trained on, they don't just get a little bit worse. They completely break. The text they start spitting out is just incoherent nonsense. So what's the culprit? What's causing this catastrophic AI amnesia? Well, the investigation leads us to this really crucial part of the AI's architecture. And it's something that creates this fascinating paradox. It's a component that is, at the same time, incredibly helpful, but also a major, major hindrance.
The main suspect is a thing called positional embeddings, or PEs for short. You see, a transformer model on its own just sees text as a big jumbled bag of words. It has no idea what order they're in. PEs are what tell the model the sequence. Without them, man eats fish and fish eats man would look exactly the same to the AI. And the most popular kind today is called ROPE.
And here is where the paradox kicks in. During training, these PEs, like ROPE, are fantastic. They're like giving the model a huge head start. It gets this built-in understanding of word order, which helps it learn the structure of language way faster and much more effectively than models that are trained without them. The researchers at Sakana AI put it perfectly in their paper. They said, quote, PEs are a key component for effective LM training, but are also a fundamental barrier to long context generalization. So the very thing that makes the model so smart and efficient during training is also the very thing that breaks it later on. It's a classic catch-22. So let's dig in a little deeper. How does this super helpful tool turn into a major roadblock when we really start to push the limits of what these models can read? Well, the problem is that these positional signals, they're based on some pretty complex math, rotations to be specific. And when you feed the model a document that's way longer than anything it's ever seen before, those rotations go into completely uncharted territory. The model has just never seen a position number that high. And that ends up warping its internal attention mechanism, totally confusing it. Now, of course, people have tried to come up with clever workarounds for this. They've tried tricks to scale or compress the PEs to keep them in a range the model recognizes, and it kind of works. It stops the model from totally breaking, but it creates this sneaky new problem. The model just starts ignoring information that's far away in the text. So it can still form coherent sentences, but it loses that critical ability to remember something from page 1 when it's on page 100. And this is where that breakthrough idea from Sakana AI comes in. They solve this whole paradox with a solution that is almost, well, it's deceptive in just how simple it is. The researchers asked this one brilliant, fundamental question. They said, what if we could use these positional embeddings to get all their amazing training benefits and then just get rid of them before they have a chance to cause problems? The core concept here, and it's a great analogy, is to think of positional embeddings like scaffolding on a skyscraper. You absolutely need that scaffolding to build the structure correctly, to put everything in the right place efficiently. But once the building is finished, once it can stand on its own, you take the scaffolding down. And this insight leads to their three-step process, which they call DroPE. Step 1. You pre-train the model just like normal, with rope, letting it do its job and build a really strong foundation. Step 2, and this is the magic trick, after that training is done, you just drop the PEs. You just take them out. And then step 3, you run a very short recalibration phase, basically training the model for just a tiny bit longer so it can adjust to working without its scaffolding.
And what you get from this simple procedure is a model that keeps all of its original performance on the tasks it was already good at, but now it can suddenly handle these incredibly long documents without any issue at all. It achieves true length generalization.
Okay, so the idea sounds great in theory, right? But does it actually work in the real world? Well, let's look at the results because they are pretty staggering.
That final recalibration step, that little adjustment at the end, it's astonishingly efficient. It is so cheap, you can just do it at the very end of a model's normal training run for basically no extra cost. And think about this. With just that tiny bit of extra fine-tuning, the model regains over 95% of its performance on the original, shorter tasks. So you lose practically nothing by taking the scaffolding away.
To put that cost into perspective, when they applied this method to a huge model, Llama 2 7B, the whole recalibration phase only required 0.5% of the original training compute. That makes this an incredibly practical solution that you could apply to even the biggest models out there.
But here's the real kicker. They tested this on Longbench, which is a key benchmark for these long context tasks. And DroPE didn't just outperform the other methods, it blew them out of the water. It improved the base model score by over 10 times. That's not just a small improvement, that is a massive leap forward.
So, what's the big takeaway here? It's that by treating a component we thought was essential as just temporary scaffolding, we can unlock a capability that has been holding AI models back for years. DroPE gives us a simple, cheap, and incredibly effective path to true long context understanding. And this all leaves us with a really provocative thought, one that could shape the future of how we build these things. It just makes you wonder, what other parts of today's AI that we think are absolutely essential are actually just scaffolding that we haven't learned how to remove yet? Thank you for joining this explainer.